Thanks for your kind words, and good to be here. Yeah, today we want to talk about 3D understanding, and I've been asked to give a little bit of a different perspective here, really talk about what we can do with the foundation models that we have already trained with a lot of money going into these models. Now, where am I here? So the setting is as follows. You want to take it out after the decision? No, I guess you can hear me all right, right? Okay, perfect. Otherwise, just let me know. Now, the setting for 3D scene understanding is really that you get a lot of views. And then you have your AI model, whatever that is, and you finally would want to have a 3D scene representations coming out of that, potentially utilize that, or throw this into another module which addresses certain downstream tasks. I guess important things along the way are representations that give you the ability to relate different semantically related scenes against another, and semantic parts in these scenes against another. That's why I've brought this particular example here, and I will also allude to that on the following slides. Now, with the recent breakthroughs in generative models, we're turning that process around. Rather than taking all of that data and outputting this 3D representation, we're now learning generative representations from which we can sample data, viewpoints, images, whatever this is from the world. The benefit of these generative models is, in that case, that we can grasp the uncertainty here, that we potentially can create counterfactuals for probing in this particular case. And the issue that we're, however, facing is that with all of these machine learning-based approaches that we're seeing here at the conference, we're pretty much going down this direction of inductive modeling. Inductive modeling, empirical based models that we abstract and want to sort of formulate about the world, we can contrast against the deductive approach. The speciality here is that in the inductive approaches we have, in contrast to the deductive reasoning, no first order principles. There is no irreducible theory that everything is based upon, but it's essentially the data. And instead of having these first order principles, you essentially have design choices that you make. And you may make different than your neighbor. And with that, the outcome will also be a different one, in contrast to such a deductive approach, which you see here at the bottom. And as a result, rather than getting a clear physical representation of the world out when we want to do 3D scene understanding, what you actually get is something which may be, hopefully, statistically meaningful, yeah, on average, whatever that means, but not necessarily directly physically meaningful. What's the consequence of that? If we have something which is at best statistically meaningful, it's clear that you would want to ramp up the size of the data on which you base these statistics, evidently the quality, and with that, typically also the size and the quality of the models. You hope that that then goes up as well. Consequence. Well, the consequence is that you need to go to domains where you have as much of this valuable data available. And I'd argue that in 3D, it's still a bit tricky. Last time I looked, there's like terabytes upon terabytes of data coming into YouTube every second. With 3D publicly available data, that's a little bit more on a tricky side. But that need not be necessarily a problem. With a lot of abundant 2D image data, video data being around, more prevalent than 3D data, let's utilize the already trained foundation models where a lot of money, a lot of compute went in, and let's see how we can utilize them as powerful inductive biases for the 3D world to do the things there which we actually want to do. With that, however, comes the second challenge. And the challenge in that case is we need to have ways to efficiently repurpose these models, efficiently translate these models to entirely novel domains and novel tasks that originally they've not been built for, in particular, going all the way into the 3D world. And I'm going to show you different strategies and how we can actually do this translation there. And the efficiency here is key because we don't have abundant resources. I guess not everybody has the full cluster of Google in their basement to retrain things anew, and that would also be wasteful, right? Once these models are there, I mean, when you become a medical doctor or whatever else, you don't throw your brain away and start from scratch. You utilize whatever you've learned and then calibrate it somewhere else. But I'm arguing for strategies which go beyond the fine-tuning, even zero-shot strategies. So here's the menu for this afternoon. I'm first going to show you how we can take emergent representations, which emerge out of current generative models that have already been trained, and how we can actually enhance them, make them more robust. Secondly, we will see how we can translate and repurpose foundation models to enter the novel domains. And lastly, we'll see how we can boost 3D models by simple strategies. Now, I guess at the core of all the understanding that we have is some kind of representation of the world, ideally some kind of semantic representation of the world. Computers just see pixels, numbers that ain't going to get us far if we want to establish relationships across scenes. What we have are generative models which spit out images, synthesize images like that. But as you know, like the first diffusion models and so on, when they came out, people happily used these models not just for generating images, but for instance, stable diffusion. After we developed that, people then came up with these diff features, essentially taking a representation layer out there and utilize that as a semantic feature representation. Semantic feature meaning that it establishes correspondences across different images, across different 3D scenes, which are somewhat semantically related. Now, features are at the core of everything that's happening in computer vision, or has been at the core of that for decades now. In the early days, we were all working on handcrafting features. Glad for you guys who are just joining the field. These days are fortunately over, where you need to fine-tune all of these things by hand. Then came the day and age where we did a lot of supervised training, later on using neural networks, whatever that was, based on some downstream task training your features. But now we're in the day and age of self-supervised learning. Now you take just like generic data, like we've done with stable diffusion, learn to generate or do whatever other task that you're seeing here. And I find particularly very striking the thing that you see in the bottom right, which are features which simply emerge out of a generative model, which has been purposed for generating images, not creating any feature representations. But nevertheless, they turn out to be very helpful. Because if you look at the different types of correspondence problems that you can address, correspondences across different viewpoints, across different classes, related classes, for instance, across different articulations of objects, or even across different levels of a taxonomy, it turns out that diffusion features, here, for instance, good old SD 1.5, give you already an edge over other strategies, but in particular, they're complementary. And if you combine them, you get a significant extra boost. I guess that makes the call for actually using generative self-supervised features here. But they're not perfect. If you look at correspondences, as long as your classes are close by, you get sort of okayish things, but here, then this dog at the bottom, no chance, that's not going to work out. Or if you see these features here extracted from a video, that's typically not giving you the best quality. In that case, you see a lot of flickering. Why is that the case? Problem one, two problems. Problem one, if you use the diffusion model to actually give you these features, front and center to diffusion models is this denoising process there. So you take your image, add noise to this image. This is running here. And as you're adding noise to this image, you finally extract the features. Now, it turns out the optimal feature you're not getting for zero noise. You get it from for a noise different from zero. And with that, you have noisy features. Evidently, there's information lost. Interesting, right? I mean, you need to add noise to get the feature. And if you take no noise, the feature, you're actually worse off. But it's clear if you're adding noise, you're also losing details. Secondly, noise is a free parameter. Depending on the task, depending on the actual data that you're looking at, different noise levels may be the optimal one. So we don't know which one the optimal one is. Which brings us to diffusion features. Taking the image, adding noise, running it through the diffusion model is going to give you noisy features, which are useful, but they lost a bit of detail, and you have this free parameter T. Naive solution? Well, just kick out the noise. Yeah, take the pure image, pipe it through a diffusion model, and you get Well, a clean feature, but one which is not very useful, right? That you need the noise in the denoising process to give you a valuable feature. Observation. You take these noisy images and you look at what the final features actually are, your semantic correspondences for the 3D world, how they actually look like. And you figure out that what you get by means of the diffusion process is actually an additive process. An additive process which takes the noisy signal, yeah, the feature here of my X0, and adds on top of that a representation of the epsilon of the noise process. So the noise gets essentially added on top of the clean features. Now we have a way towards the solution. We simply copy the diffusion process, which you see here at the bottom, and then try to and this copy here now gets as input the clean image, no noise added there. So finally, we have a network which sees the true reality there. Then you want to minimize the difference between these two outcomes here, between the noisy and the clean features. And because we have the additive process, you have a chance of optimizing that correctly. Issue is still that this process at the bottom is trained and adjusted with different time steps there. So we might now have useful and noise-free features, but we still don't have a single feature. To solve that, we added an additional projection layer here, and now the free parameter gets piped into this projection layer, not anymore into the feature extractor. You optimize that over all different time steps, and essentially the features are the aggregated features that you're learning with that, the aggregated features over all different noise steps. And with that, you get features which are significantly cleaner by just training for roughly half an hour on a single A100. Your correspondences are significantly better. Left, standard diff. On the right-hand side, you see that you get true semantic correspondences going far across an individual category. And last off, these diffusion methods give you state-of-the-art performance and outperform, and you can combine them with different feature methods based on different backbones, so not just one version of SD or whatever, different ones that you can use there, and you can apply them to a whole number of different tasks and see benefits. If you're interested in learning more of that, Friday morning, we'll have an oral session 1C, going to have a talk, and afterwards a poster. Please come around, ask questions, and my doctoral students will like to talk with you about that. Now, secondly, when we now have trained these generative models, how can we utilize them for entirely different modalities and tasks? And how can we repurpose them and add additional control into this process when we actually repurpose models? Well, the first thing that comes to mind are probably adapter approaches, and rightfully so. Adapter approaches, you see here a whole bunch listed, which gives you the ability to take an already trained generative model and fix certain aspects, and with that gain control over this model, and just throw in here a text prompt and fix, in that case, the geometry of the scene. And then you can alter the text prompt, but the geometry will always stay put as it is. Problem with that is that there's not one adapter to rule all sorts of conditioning. It turns out that there's an invisible divide here, an invisible divide between the approaches at the bottom, which actually have exert fine-grained control over the structure, the spatial structure of the scene, and at the top, the ones that give you more like the overall context, style, or whatever that is. And there's not one adapter to tackle all of these tasks. Our approach, therefore, is to propose a method to give you an efficient, flexible, and an approach which is model agnostic, which you can slap on top of whatever generative model that you have, which can combine both together. Vertical axis here, the spatial structure, the fine-grained manipulation, and on the horizontal axis, the global context. And you see we are here in the top right corner, and the disk indicates that our approach is having significantly fewer parameters, easier to train in this particular case. Now, how do we get this going? Well, here you see the standard low-rank adaptation, a standard LoRa approach, where you take a generative model on your left, and you add a bypass to this generative model. A bypass, which is an encoder-decoder architecture. Now, so far, however, you need to adjust and train this bypass for every task anew. Our observation is that we're having a low rank adaptation. And we now introduced here an affine projection in the low rank space and only train or adjust then this green part there, which has the benefit that we now get a conditional LoRa. LoRa, which you can train once, and then you can swap and alter the conditioning based on the actual input that you have. Means that we add two neural networks here, and this is then what you want to train. One which takes care of the local and one which takes care of the more global context of the scene. And now you can, on the fly, in a zero-shot manner, throw different data in after training it once, and then adjust, change the conditioning of the scene in a zero-shot manner, adjust the output. Meaning I can take structure, and get this deer-like animal here, this toucan here, if I take the overall style or mix and match them somewhere in between, however I want. But not only that I can get structure and context in there, it also works with all sorts of modalities that you may want to have if you want to exert 3D scene understanding. You can utilize the overall context of the scene, depth maps to give you an idea of the 3D structure, edge maps like AGD here, or some kinds of posture representations. Now with that, let me make the transition into the 3D world and show you how we can repurpose a 2D model, which has been just trained on 2D images, repurpose such a foundation model over to do reasoning about the 3D world. Reasoning about, for instance, depth in this scene. And we're looking here at approaches for monocular depth estimation. I'm going to show you an approach which is generative, starting from generative model, which is fast and giving you really good performance. Good performance, well, the name of the game are typically here discriminative approaches, which are reliable, but somewhere coarse in their depth estimation, but more importantly, generative approaches give you an estimate of the uncertainty. You have an ensemble that you can sample from, an estimate of where the approaches are certain, where they're actually not so certain. Now, after diffusion models came really out, there have been first really nice suggestions of generative approaches like Marigold here, for instance, but they relied on standard diffusion processes like stable diffusion. And with that, you get a fairly lengthy trajectory. Trajectory because you're starting essentially with pure noise and turning the pure noise into a depth map. Our suggestion here is utilizing flow matching. Flow matching, rectified flows, give you a straightened trajectory, and with that is a fairly fast approach, which can start not with just pure noise and no signal there, but with a noised version of your input image. And I guess with that, we directly see that this trajectory at the bottom there is significantly shorter and retains more of the original signal. And with that, we in a low NFE regimen are actually getting better performance. Now, how does this repurposing, this translation of already trained 2D on RGB images, 2D diffusion model work, and how can we repurpose it for the sake of 3D? You take images, pipe them through Stable Diffusion's latent encoder, and you get a latent representation of the image. So far, so good. This is what everybody does. If we had a latent representation of depth, we could pipe it through Stable Diffusion's decoder because that's fairly generic, depth map image, whatever, right? And you take this latent representation of depth, if you had it, pipe it through the decoder, and you get a real estimated depth. The problem is we have this gap between these two. And that's for training while we're resorting purely on synthetic data. No single real image going in, just synthetic data. We have image depth map pairs, one-to-one correspondence. You pipe the depth map through the latent encoder, you get a latent depth map, and then you have bridged on that part the gap between. But there is an issue. The issue being that there is not a one-to-one correspondence between an image encoding and the depth map. There are two situations. The first, several images can actually have the same 3D structure, the same depth. I can change the color of my shirt. My posture would still be the same. My 3D nature would still be the same. That we can fix. We can augment, can sample, and we have a generative model, several versions of the image and retain this 3D structure, essentially redress me, and then That's okay, many to one. The opposite direction is tricky. You can have translucent objects, reflections, and so on, where you have a single image, but several plausible depth maps for that. That we cannot create. If we had this, then we would have solved the problem. We would have a true understanding of the multimodal nature there of depth. How can we address that? We cannot sample there several from the depth map. Well, what we can do is create several of these augmentations, these many-to-one augmentations. And then if we do that with a lot of images, if we train there on several of these images, we observe that some of them, especially in their augmentations, will get close to another. You get this purplish area in between. We have two images, two RGB scenes, which are almost interchangeable, very close, but their corresponding depth maps, which you have, are distinct and separate. And now we have one purple there, too many blue and red images. So we have many to one, one to many, and that you can piece together and get a many to many. How do you piece it together? You throw a flow matching approach, and that now is your workhorse for the translation, something that I can recommend. I find flow matching for that super helpful. A flow matching approach, which you feed the noised image, and in addition to that, you add the pure latent as a conditioning signal, pipe it through the flow matching approach. Flow matching approach as a bijection helps you then to do the translation in that case without further alteration. And with that, you get an approach which improves over generative approaches that we had so far significantly in terms of the time, works in a low function evaluation regimen really well, and in terms of discriminative approaches is also showing you great performance in terms of delta 1 accuracy. And the size there of the disk indicating that we only trained on synthetic data compared to Omni data and other approaches which require orders of magnitude more of real data. So with that, you obtain an approach which is generative, which is fast, generative, giving you also confidence, which is fast, real-time performance, accurate and detailed, and you have easy training because you need only very few synthetic training samples. Now, last, and then I wrap up, I want to show you some recent work of ours, how we can take Gaussian splatting and make the approach faster and provide you higher quality there. And it's an embarrassingly simple approach that I'm going to show you. But before we get there, let's briefly look at how 3D Gaussian splats work, and in particular what the issue with them is. You take a structure from motion approach to initialize your Gaussians. You get them here. I get a few Gaussians in there. You project them and run it through a differential rasterizer to actually get then your splatting in a 2D image. You compare that against a real image, you get a loss. Well, your splatting is not perfect. You backprop that through the differential rasterizer, and with that, you update your Gaussians there. But you notice, you do this as often as you wish, but you notice that finally you don't get your arrow down anymore. Why? Because you're just running out of Gaussians in the right place, and what you then need to do is you need to densify the Gaussians, add more in that particular case. Now, there's an issue with splitting up these Gaussians here, and you see this here in the high frequency details of the scene. And the issue is that several of these pixels, which you see here on the left, try to own, you see that in the middle, the same Gaussian, because you initialize it with your structure and motion approach with like some huge Gaussians that you have there. And with that, your optimization can do whatever it wants. The same Gaussian gets pulled in different direction, and essentially your optimization approach is just sitting idle in certain areas, especially high frequency details, and wasting time while there's essentially no chance for it to really go anywhere. That's why we suggest in that case an approach which gets you a significantly better initial setup of your Gaussians, essentially a spot-on initialization, which eliminates the densification altogether. No densification in 3D Gaussian splats anymore. For that, we need current state-of-the-art dense matching triangulation approaches like Roma. You see a few others that we compared against here. They're also working well, as long as you're not using some crappy old whatever, like optical flow-based approach, which is evidently not suited here, like Raft, but all the others are almost equally fine. And with that, you get 3D localization and the size of your Gaussians. You can initialize them directly based on the match points and their camera rays, and you can average the colors to actually give you this parameter. And we see then that in our approach, the Gaussians are initialized significantly closer to the final location where you actually want them to go. With that, the individual Gaussians don't need to travel that far anymore. In orange is how far they have to travel in our approach. Blue is like standard Gaussian splatting. You see it here indicated on the x-axis that ours in orange compared to the blue are traveling orders of magnitude less from their initialization to where they eventually need to go. That evidently means that things are going significantly faster. And you see it also here, bottom right, the initialization being significantly crisper than what you get in standard 3D Gaussian splats. And with that, x-axis being time, horizontal axis being time, the vertical axis being the performance, the quality that you achieve. You see in orange here, our curve being faster, being better on their respective other axis than the other approaches that we've seen in that field so far. So it's outperforming both the speed or the quality optimized approaches, giving you like their half an order of magnitude improvement, 40% less Gaussian splats. Go to our Hugging Face demo. You can try it out there with your own images, just with your camera, take pictures and try it out. And you're gonna see here, it's an example, 9 seconds compared to 20 seconds. And if you look there to the grass, a bit hard to see from the back, but on the right-hand side, you can see all the trees and grass and whatever. On the left-hand side, not. With that, for the organizers are getting itchy here, let me wrap up. We've seen 3 things that I wanted to address. First, generative models are really great in giving us emergent features that are super helpful when it comes down to 3D scene understanding, a representation which can really establish 3D correspondences. And this approach, which we coined clean diff, is an approach which can take the diffusion processes, which are great for that, but make it eventually noise-free and also parameter-free, get rid of this T parameter. And second, we looked at how we can translate 2D image models, which have been just trained on 2D data, translate them to different tasks, especially into the 3D domain. We first looked at approaches which add very conveniently control to these representations by means of the conditional adapters, which you can in a zero-shot manner on the fly very effectively then alter and adjust to different new conditioning signals. Depth FM, how flow matching as this bijective approach there can bridge between different modalities, between diffusion models that are already trained in new modalities, and last off, how we can actually improve on 3D models by eliminating the densification that we've seen all along. With that, let me thank my wonderful team that made all of this work possible. Let me thank you for your attention. If you have any questions, I'm still here. Any questions?
I have some problem. It's just interesting.
Yeah.
So we can earn classification by visualize the Gaussian easily, but for the dynamic, how can we with some local division?
Yeah.
How can we visualize the 3D Gaussian identity?
Yeah.
There's
okay. The evident next question, like we just got this work out. How about the next bigger task, going to dynamic scenes? This is something that we're presently working on. There are approaches which are also robust with respect to parts in the scene shifting and changing. But yes, it makes the problem evidently a little bit more tricky than what we have. But we see good indications that it's also working in that angle. I guess there's somebody else, or you get follow up.
Question on how was the error computed on features that you presented different layers had different errors? So how was that?
You mean for clean diff?
Yeah, for the clean
Let me see if I have those stats in here. So that was PCK that we measured here for the different backbone.
That like minimum.
Ah. Okay. Yeah. This year's, you take the time step, and in that case, we took the feature. We estimated both, like one being also PCK in that case. You're changing the noise, but you can also go for different measures if you prefer. But whatever it is, I mean, that's what you essentially observe, right? Yeah.
So we many to one.
Yeah.
So in that case, are there like heuristics on samples to a day?
How many samples you take?
Or
Well,
is it like more the better?
It depends on your data distribution, right? How far it's actually spread out, how much variance we're talking about. What you want is you want sufficiently much so that you can actually cover it. And in the, what's that, if you want to produce essentially this one-to-many approach, you want them to get close enough together. That depends on how many samples you already have and how near they are. If they're super far away, you evidently would want to sample them.
So as you said that there were like few thousand samples that you did.
Yeah.
Does that mean that like diffusion space is very narrow space and then we have few samples are enough, few thousand samples are enough?
So that's the train set here that you're referring to, 60,000 samples that we're having, yeah, and then on top of the usual augmentations. That means, I guess I would draw a different conclusion there. That means that stable diffusion, the 2D image model, gives you already a very good inductive prior just from the 2D domain, which you can then easily transport over to another domain. There have been today other keynotes people that utilize just stable diffusion out of the box for material transport, for instance, stylistic approaches and so on. It's interesting what is, and Diffit has shown that with the feature representation, what information is already there. And I guess that is, if any point in this talk, in this keynote, that would be the point that I would want to make there. Although you're interested in an entirely different domain there, like depth and 3D structure, in the 2D information, although it's never been trained on that, there's a lot of information in there which we can utilize. And just with a few samples, 60,000, so only synthetic data, right? No real image there. And everything about real world, that's already there in the 2D image model. That's getting translated over to the other. So I wouldn't, in that case, say so much about like the variance that you're having there, but more like you have a very sort of versatile model, which is also well versed in reality, which helps you then translate over.
Yeah, you're working with insights.
You're welcome.
So a question on the clean diff. So you show basically the curves that you show that basically the optimal feature are the one that are taken middle diffusion steps, right?
Well, in which point that depends on the task that you're going for.
Is this something that is analyzed to different diffusion model on testicle?
No, I later on had these bar plots there. We trained it on we evaluated on a whole bunch of different backbones, diffusion models that we had there on different tasks, and also different diffusion feature methods. So essentially everything that you could think of, we actually played out.
They all have the U.
Yeah, you get that, yeah. Well, just to explain this, right? You have a diffusion model. If you take no noise there, what should your diffusion model do, right? You need to add a little bit of wiggle room, so to speak, add noise to it, so that your diffusion model has a little bit of leverage and leg room essentially to do something with a feature. And that's why you need this bit of noise there. They differ, and it differs on the task, like what the optimal operating point is. But all of them need this, because without that, there's no diffusion model anymore, right? If you that's the naive solution that I showed. No noise in there, clean image in. Well, then you get not very useful features. Yeah, you're welcome.